Welcome to section 5.1. I'm just going to jump right into the definition of eigenvector eigenvalue. Suppose you have a square matrix and lambda x equals ax for some non-zero vector x and some number lambda. Then we say x is an eigenvector corresponding to the number lambda, and lambda is an eigenvalue. What that means geometrically is that x and ax lie on the same line, and I'm going to show you that with an app. So here we have a visual representation. I've got a vector x in red and ax is in green. Don't worry about the numbers, but look at what happens when I get x right about here. Ax lines up with x. It's some multiple of x. And notice that if I stretch x out, I'm still getting a multiple of x, or if I shrink x. So any multiple of x will also be an eigenvector. And then there's another one over here. Now, not all matrices have real eigenvector eigenvalues. So let me show you another one. Okay, this is the rotation matrix that takes a vector x and rotates it by 90 degrees. You can see clearly here that no matter what x is, ax and x are never going to line up. Okay, back to the lecture. Suppose we're given a matrix and a vector v, and we want to know if v is an eigenvector. Well, that's a pretty simple computation. We want to know, is AV equal to lambda v for some lambda? So we can just do the computation here. I multiply this out and I get negative 2, 6. Well, no, that's not equal to lambda times negative 1, 1 for any number lambda. So no, okay? So you guys can show that u here is an eigenvector of A and find the corresponding eigenvalue. Pause the video and try that out. Okay, hopefully you did that. AU is this computation, which gives us negative 2, and that's negative 2 times the original vector 1, 1. So yeah, 1, 1 is an eigenvector, and its corresponding eigenvalue is negative 2. This example I just showed you on the app. This is the rotation matrix, and it has no real eigenvectors. Okay, so if we're asked to find if a vector is an eigenvector, that's a straightforward computation. But if we're asked if a number is an eigenvalue, that's a little tougher. And so here's what we do. We want to know if lambda equals 2 is an eigenvalue of A. So the question is ax equal to 2x for some non-zero x? That means non-trivial solution. Okay, move the 2x over, and I'm right here. That corresponds to this equation here. Does this equation have a non-trivial solution? So what happened is, when I factor the x out of this equation, I can't just leave the 2. I can't subtract 2 from A. A is a matrix, 2 is a number. So I write 2 as 2 times the identity, and that's a computation I can do. So let me just jump down before we do this computation. Let me just jump down and summarize. This is the first example we did. To see if a given vector is an eigenvector, just check if AV equals lambda v for some lambda. This is the computation we're about to do. To find any single eigenvector corresponding to a given lambda, you're going to solve a minus lambda I x equals 0 for a non-zero x. So what we're doing is solving a minus 2I times x equals 0 for a non-zero x. And then just let me jump ahead to the next section. To find eigenvalues, which we're not ready to do yet, but we will eventually, we're going to solve the characteristic equation determinant a minus lambda I equals 0. Now, where did this come from? A minus lambda I times x equals 0 has a non-trivial solution if and only if the determinant of that matrix is 0, and that's by the IMT. Okay, so let's go back to our problem here. I've done most of the computation for us. This is A, and this is twice the identity. And I subtracted, and I got this matrix. So what I do is I reduce that matrix augmented with 0. So that's what I have right here. This is the augmented column. It just took one row reduction to get to this matrix. So now I'm ready to write down the solution. I'm going to start at the bottom. X2 is t, x1 is negative 2t. So my solutions look like t times negative 2, 1. Now, any non-zero t will give me an eigenvector. Will give eigenvector. So let's take t equal to 1, and then we would get v equal to negative 2, 1. That would be an eigenvector corresponding to lambda equals 2. So lambda equals 2 is an eigenvalue. So the answer to the question is yes. And here's one corresponding eigenvector. And we can check it. Let's check. We need to check that A times V is twice V. So the original matrix A is 3, 2, 3, 8, multiplied by negative 2, 1, and we get negative 4, 2, and that is indeed twice negative 2, 1. Okay, so now let's talk about eigenspaces and their bases. If you have a matrix A and a corresponding eigenvalue lambda, then the eigenspace corresponding to that eigenvalue is a vector space. And it is the vector space defined by this. It's the null space of A minus lambda I. So we're going to be finding a basis for the null space of A minus lambda I for given lambdas. And that's the sentence in red. So let's do it for this example here. We've got a 3 by 3 matrix, and lambda equals 2 is an eigenvalue, and I'm told that. I don't have to verify that. I want to find a basis for the eigenspace. So here's the matrix A, here's 2i, and I subtract to get this matrix, and I want to augment that with the 0 vector in order to find a basis for the null space. So I went ahead and did that computation. So now I'm ready to write down the solution. So this is just exactly what we did last time, except now I don't want a single vector, I want a basis for the null space. So x3 is free, it's t. x2 is free, it's s. And x1, if I look at this top line here, that tells me x1 is s plus t. So my solutions look like x bar equal s times 1, 1, 0 plus t times 1, 0, 1. So a basis for the null space of A minus 2i is the vector 1, 1, 0, comma, 1, 0, 1. And I'm going to name these V1 and V2 because I'm going to reference them in a minute. Okay, pause the video and find a basis for the eigenspace of A corresponding to lambda equals 4. So you're going to do the same computation I just did, except here you're going to have 4 times the identity, not twice times the identity. Okay, I'm not going to go through the solution because it's on the last page of the lecture notes. So check your answer. You should have gotten basis, single vector, 0, 1, 1, and let's call that V3. Okay, so make sure you go through and you can do that. So let's look at this theorem now in terms of V1, V2, and V3. The theorem says if you have eigenvectors corresponding to distinct eigenvalues, then they're linearly independent. So that tells me that if I group V1 with V3, those two vectors are linearly independent. V2 is also linearly independent with V3. But I can make a stronger statement, and that's right here. I can toss them all into a single set, and that set is linearly independent. Okay, properties of eigenvalues and eigenvectors, and I've written the proofs out for you, which you can read on your own just to save time and make the video a little bit shorter. The only one I'm going to look at in detail is the first one, but let's just go through the others. The eigenvalues of a triangular matrix are the entries on the main diagonal. That's pretty darn nice, and there's an example of that right here. A is invertible if and only if 0 is not an eigenvalue. All right, that updates our IMT. So if you flip to the IMT here, you can see I've added one statement. So now we're up to S things being equivalent. 0 is not an eigenvalue of A is equivalent to A being invertible. Okay, and then if A is invertible, then and lambda is an eigenvalue of A, then 1 over lambda is an eigenvalue of A inverse. And the eigenvalues of A and A transpose are the same. So let's look at this first one a little bit more carefully, and just in the case of A squared x. So let lambda be an eigenvalue of A with corresponding eigenvector x. We're going to show that A squared x is lambda squared x. What that tells us is that lambda squared is an eigenvalue for A squared. And that's what number 1 says. So here's the starting point. We're given that AX equals lambda x. Multiply both sides by A. So on the left, I have a squared x, and on the right, I have a lambda x. Well, I can pull that lambda out and write ax, but ax is lambda x, so that's lambda x, which is lambda squared x, which is what I wanted to show. So the interesting thing is that a and a squared share the same eigenvector x, but the eigenvalue is different. Okay, and you can read through the rest of these notes on your own, but that is the end of what I'm going to do for this section.